Hello guys, and welcome back to Introduction to Number Theory. In the previous video, we defined a polynomial called continuant. Well, actually it's not one polynomial, but infinitely many polynomials that have some common properties. In this video, we will start studying properties of these polynomials. So first, let's consider a certain example of a continuant. Say continuant of order 4. Variables are x1, x2, x3, and x4. And this index here always denotes the number of variables in the continuant. And we know that continuant is a polynomial gained from the product of all of these x's by adding monomes gained from this product by throwing out pairs of x's, pairs of neighbor x's, actually, in all possible ways. So, for instance, if we throw out the first two x's, we'll gain x3, x4, and similarly, we can get x1, x2. But we can never get x2, x3, because we cannot throw out x1 and x4. It is forbidden. Pairs of x's, well, x's in these pairs must be neighbor. So, is there any other way to throw out pairs? Well, actually, we can throw out this pair, x2, x3. We will gain x1, x4, and we can throw out all of the x's, because this pair is a pair of neighbor x's and this pair also. So if we throw out everything, we will have not 0 but 1. Let me just check. 1, 2, 3, 4, 5. That's it. So this is continuant order 4. And now notice that some of these summands contain x1 and some don't. So this one contains, and this one contains, and this one. What will happen if we take this x1 out of the parentheses? We will have x1 multiplied by x2, x3, x4, and plus x2 and plus x4, and we will have several summands that didn't contain x1, and these are x3, x4 from over here, and 1. Well, there don't seem to be any other such summands, plus 1. So what do we have here? Just look at this expression. What is it? Well, actually, it is also a continuant. It is k of order 3 of x2, x3, and x4. Well, indeed, if we take the product of these x's, well, here it is, and we can throw out the first pair, so x4 will be remained, and we can throw out the second pair, so x2 will remain. And that's it. And this expression here, well, is also a continuant. It is k2 of variables x3 and x4. Well, indeed, we can take the product of these variables and either throw out no pairs or throw out one pair that there is, and one will be left. One, I mean as a number. So something similar can be done with any continuant, and there is a recurrent equation in continuants, Kn of x1, x2, x3, and so on, xn, is equal to x1 multiplied by, just as here, kn minus 1 of variables x2, x3, and so on, xn. So this is the part of the initial polynomial, of the initial continuant, that contains x1. So this is the part that contains x1. And we have a part that does not contain x1. It is equal to also a continuant of order n minus 2 in variables x3, x4, and so on, xn. So this is a general rule. And the proof of this rule is just the same as we did for K4. So first we need to take all the summands, all the monomes that contain x1 and realize that x1 is multiplied by a continuant. And then take all the summands that do not contain x1 and also realize that this thing is also a continuant. Well, it follows from the definition of a continuant, because if we take x1, then all that is left is indeed gained from this product of x2, x3, and so on by deleting pairs of neighbor x's. And also, if we take something that does not contain x1, well, this part is a bit more tricky. How come a monome in a continuant can turn out not to contain x1? Well, only if x1 was deleted and thrown out. But deleting x1 inevitably causes the deleting of x2, because we have a product of all of the x's, x1, x2, x3, and so on, xn. And if we want to delete x1, then it can be done only if we delete this pair here. So all that is left will be gained from this product by deleting some pairs of neighbor x's. Okay, so now that we have this recurrent equation as a property of continuance, let's consider a fraction whose enumerator and denominator are continuants, namely k of order n plus 1 of variables a0, just as in continuous fraction, a0, a1, a2, and so on, an. So notice that n plus 1 is the number of variables. Well, indeed, variables are from 0 to n, over, this is the numerator, the denominator will be kn of all of these a's, but a0. Okay, so if we transform the numerator according to the recurrent equation, we'll gain, let me write it here, we'll gain a0 multiplied by kn. Well, we understand that here there will be all the variables except for a0 plus k n minus 1. Well, here we will have all of the a's except for the first two, because we thrown them out when we wrote this part of the continuant. And will not touch the denominator, it will still be kn of all these variables. And now notice that this can be transformed into a0 plus a fraction k n minus 1 over kn. And now transform this part, this fraction, into 1 over kn of a1 and so on an over, well, this over is more important than this one, so this one is main and this one is just inside the denominator, over k and minus 1 of a2 and so on an. And just notice that here in this denominator we have the not exactly the same but very similar expression just we had in the beginning. So it is a fraction of a continuant over continuant. So we can continue to transform these fractions and eventually we'll come up with something like a0 plus 1 over a1 plus 1 over a2 plus and so on, and eventually this will end with 1 over an. For now, all these a's are just variables. So we come to a conclusion that the continued fraction, a finite continued fraction of n plus 1 floors, can be transformed, if you just reverse the direction of these transformations, can be transformed into simple fractions where the numerator and the denominator are continuants of these elements. It doesn't matter whether these elements are numbers or variables or some polynomials or whatever. This was the main property of continuance, the recurrent equation and the connection of fractions of continuants with the continued fractions. In next videos we will come up with some other properties of continuance, but most of them will follow from this one. Stay tuned.